Now it's time for hands-on Arduino. Okay. In this section, we're going to give an example in using a number of facets of things that we've been talking about. So the problem that we're going to look at is this problem here. Okay, we're going to set up an interrupt that triggers every 1.0 seconds. Okay, so it's going to trigger every 1 second in 1 second intervals. In the interrupt service routine, we want port D pins 2, 3, 4, and 5 to be read. So in the interrupt, so every 1 second, these pins are going to be read. If any two of the pins have changed since the last time it was in the interrupt service routine, then pin 6 is set to 1. Pin 6, digital pin 6 is set to 1. Otherwise, it is set to 0. Okay, so if any two pins have changed since the last time, so notice by saying any two pins, it actually means that I could have 3 pins that change since the last time. Okay, but if no pins or just 1 pin change, the light does not go on. So basically, what's going to happen is if you flip the switch, or if you have 4 switches, if you flip one switch, for example, any one of the switches, if you flip one switch, it'll do nothing. If you flip 2 switches at the same time, it will, the light, or rather, this pin will get set, and then 1 second later, it's going to check again. If you haven't changed any more, then the light will go off. So basically, the light will stay on for 1 second, and it's checking every second whether the light will go on or not. If in between 1 second and the next, 2 switches have changed, then this pin will be set. And so in our implementation, we're going to use an LED on that pin so that you can see what's actually happening. Now, there are a number of ways of approaching this problem, and from our perspective, in terms of programming, we could do all things in Arduino code. We could do part C and part assembly. So when I say all Arduino, I mean C. We could do part C, part assembly, and here we could do all assembly. So these are the options that we have. I'm going to choose the all assembly. It would be very straightforward to do a lot of this using the Arduino code, the C code directly. And we've shown some examples that involve part C and part assembly, and so we're going to just do everything all in assembly. So that's where we're going next. So in our problem, we need the thing to trigger an interrupt every 1 second. So basically, we're going to use a compare match. That's one of the best ways to do timing. And so here is our formula for calculating the compare match register value that you need. And so the clock frequency, 16 megahertz, interrupt period in this case is 1 second, and then prescaler is one of these values. Okay, 1, 8, 64, 1024. Okay, so if we actually do this calculation for these prescale values, these are the values that we get. These are the compare match values that we will get. And so you can see these are actually fairly large values. All of them are greater than 255, which means if we're going to implement this on an Arduino directly, we actually need a counter that can count above 255. And so that basically is going to require that we use a 16-bit counter. So there's only one 16-bit counter. And as you can see, for a 16-bit counter, 65,000 is the largest magnitude, 65 something. And so 6200 is the largest, is the one that we want to use. That's the one that's below the 65,000. Okay, And in terms of, and so again, that's going to require timer 1, which is a 16-bit timer. And this number then is this in hexadecimal, F423. So we now know that we have to use timer 1. Okay, that wasn't specified to us in the problem, but now we know we have to use timer 1. And we know if we use a compare match, then that is the value that needs to go into the compare match register. So in terms of setting up the problem, we need to look at the registers that we need to set. And as you can see, for this problem, there are quite a few registers we need to set. So let's take a look at them. So timer counter control register 1A, we're going to set it to be all these values. This is kind of the default value, which gives us normal mode, and so normal as opposed to pulse width modulation, and no, actually this is normal. So this is normal with respect to the what's called the CS pins. Okay, so there's the normal mode is the simplest mode with that. Okay, the B register, I'm going to set it so that it has no ICR associated with it, and the prescale is going to be 256. Okay, and so that gives me this value here. That's what I need. The TCCR1C, we're going to have all zeros. That means we're not going to do any forced outputs. Here are the output compare registers 1A and the high byte and the low byte. So there's the 4F23. They need to go into those registers. Our timer interrupt 1 mask, basically we want a single interrupt, and we want it to interrupt with respect to the output compare match A. So we set that interrupt bit. Okay, so that's all the timing stuff we need to set. So if we set that, we will get an interrupt occurring every 1 second. All right. Now we set up the bits that we need. So data direction register, bit 6, we need to set it as an output. And since these other bits, bits 2 through 5, are set as input bits, if we write to port D 1s to those bits, that will set pull-up resistors. That means our circuit doesn't have to have its own pull-up resistors. We can use the internal pull-up resistors. So that simplifies the wiring. Okay, so those are the registers we need to set, and those would go into our setup program. Next, we see that since a change in any 2 pins is the condition for bit 6 to be set, then the opposite is that if only 1 bit or no bits are changed, then bit 6 is not set. So that is actually a fewer set of conditions that are required than actually checking for pairs and then triples and then all 4. Okay, so if you only have to check that 0 are set, or bit 2 is set only, bit 3 is set only, bit 4 is set only, bit 5 is set only. Okay, so if I define X to be the entire port D, which is that first set of digital pins 0 through 7, if I AND that with this number so that I just mask off bits 2 through 5, I'm going to call that X, and I'm going to define a global variable XP as the past value of X. Okay, and if I take these 2 values and I exclusive OR them, okay, so that basically checks to see if there are differences between any pins. Okay, so if there's any difference between pins 2 and 5, the pin associated with that will be set. Okay, so now we're only going to check if we have no pin set and 1 pin set in each of the 4 possible places. So if no changes occur, then this exclusive OR is going to give me all zeros. If only bit 5 changes, then this is the number that I will get when I do this exclusive OR. If only bit 4 changes, this is the number I get. If only bit 3 changes, this is the number I get. And if only bit 2 changes, this is the number I get. So these are the possibilities I'll get. In any of these cases, the bit 6 will be cleared. Otherwise, the bit is set. Now, it looks like there are 4 possible ways in which the bit 4 possible ways in which the bit will be cleared, which means there are 12 possible ways in which the bit would be set. So it seems like, just if you look at the number of the differences between those two, 4 versus 12, it seems like the bit is going to be set most of the time, when in fact, actually, that's not true. Actually, this condition right here, when there are no changes, is probably most likely going to be the most common case. Okay, that's going to be the most common case. In other words, the system is going to, for us to flip the switches, it's not that swift for us to do that, and so most of the time it's going to be sitting there and waiting, and while it's waiting, no changes are happening. So this is actually the condition that is most likely to happen. Right? So now this is the theory back behind our problem. We're now going to look at our software, our code. So here is our INO file, and you can see it's very informative. Well, we had decided we're only going to use assembly, and so this is our INO file. There's nothing to it, literally. So when we use just assembly, we only need really the S file. We don't need an H file either. So go over here to our S file, and so our S file starts off, and in our S file, we first include this this H file, this header file, that defines all the I/O ports for the AVR, and so this is helpful in that it allows us to use, for example, the register names instead of the address, and that just kind of is, a helpful thing. And also, it's informative. It actually makes our code more informative than just giving some address. So if you just give it the address, it's like, okay, there's an address, but then you have to use the table to look up the address, and if you're trying to debug the code, then you have to go backwards to get the address. Now, the tricky thing about using these addresses is that these addresses in the AVR are the memory address, not the I/O address. And so if you remember, there's a difference of 20 between the two, and you can definitely get snagged. Incidentally, I want to say right up front, the code you're going to see here now was not developed in 10 minutes, okay? I didn't just type this all out, boom, 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 and get it working the first time. What you're seeing is actually code that has been debugged, painstakingly debugged, and is found to be working, okay? So when I say it's completely debugged, I'm not even saying it's completely. All I'm saying is it seems to be functioning properly. I haven't had any hiccups since I started it, but so if you think that I just went through and did all that theory and then just pounded out this code and it all worked the first time, no, it actually has taken hours to get this working. But part of the reason is that there are certain things about all of this that I just didn't know up front, and so I often learn something each time I undertake a new project that's not like anything I've done before. There's usually some snag, some little thing that kind of gets me, and I'm sure you may find a similar thing. This whole process is not documented extremely well, and so there are little hidden gotchas from time to time that you come across. So I came across my share in developing this. Now at least I know all the gotchas for this particular program, but that's a challenge. And so I'm giving you the fruits of my labor, saving you the hours upon hours of debugging, of headache inducing debugging, and I give you all the choice nuggets that you need to be able to do your program successfully. Okay, so I include that. Then I have my data, and my data, I defined this variable, port D, the past value. So remember when I was going through the theory portion of this program, I had the port D that was masked, and that was what I call the variable X. So if you go back some slides, you'll see that. And actually the previous slide. And then there was XP, the past value of X. So this really serves the place of XP. Okay, and I only need one variable. I don't actually need X as a variable defined or port D defined. So I'm just calling it port D, P standing for past. Okay, and it's a global, 1 byte. All right. Then I move on to the text portion of my code, and I defined the 3 global functions: setup, loop, and then this ISR function associated with timer 1, compare match A. So that's the ISR function that I'm going to be using. And so notice here we can just define the setup and the loop functions. We don't have to use setup and loop in the Arduino IDE. We can use them here in the assembly portion. And so here's the setup. Boom. I do all this stuff in the setup. And then I return. And that's the setup program. Easy as pie. So if you were to actually take this whole thing and you were to disassemble, if you were to compile this and then disassemble it, you would basically find all this code in the disassembled printout, and it would be under setup. And in the full code, so what we supply to the Arduino IDE are several subroutines. We have setup, loop, and then whatever other subroutines we may add. That's what we contribute. The actual program that gets put onto the Arduino includes all of the startup code, what happens on reset, and there's actually tons of other stuff that gets added in to this. You will see these little sections in there, but you'll actually find this code directly in there. And so setup is just one of the routines within the entire program. The program actually uses, like in C, main, the main function, and so in the actual code that gets downloaded to the Arduino itself, there is actually a main function, and the main function first calls the setup routine. Then it actually has an initialization routine. It calls first, and then it calls the setup routine. Then it calls the loop, and then it does some other things as well. So that's how it is. If there's time, I'm going to help you to see how to do the disassembling, so that you can actually look at your entire code in the Arduino, that the Arduino actually downloads onto your Arduino. Okay, so here's our setup program, and now we're going over here to here is our setup routine, all right here. The other routines are here. So here's my loop function. So you can see the loop function is very simple. It's just it's like the open and close braces in the C. It does nothing. And then here's our interrupt service routine vector. Okay, and there's that function. So let's take a look at what all these guys are doing. Okay, so we'll start here. So if you recall, back in our theory portion, we had all of these registers that we were setting. Okay, so TCC R1A, R1B, R1C, and all of these values. So that we needed to set all of these values. All of these values get set in the setup routine. So as we go through here, we can see first TCC R1A, and notice, so STS basically says store into memory. So this is actually the memory location for that register. Incidentally, when you can always use the memory location if you use STS. If you use STS, you have to use the memory location. You can't use the in or out functions using the memory locations. And so, but the STS you can always, so since these are defined as the memory locations, you can always use those. However, it is faster if you use, for example, out and in with the if you use the out and the in using the actual I/O address, it's actually faster. So sometimes we'll use the out and the in, and when we do, we have to use the I/O address, not the memory address. So here we first, so notice if you remember, TCC R1A was actually all zeros. So remember R1 is a value that a register that is always set up to be 0. So actually that's part of the initialization routine that the Arduino goes through. At first, one of the things it does is it zeroes out R1. So R1 we can just use as 0. And so basically all this is doing is writing zeros to this register, which is the default value anyway, but here we're making it explicit. Okay, then this value here is the value we wanted to go into TCC R1B. So remember, this sets up the 256 scalar, prescaler. And so we load that into register 18, load register 18 into that register. So notice here I'm not doing anything particular to keep track of or saving the status register or saving register 18. We're just going right in. We're just starting to use register 18. Remember, register 18 is one of the ones you can leave messy, so we can do this in our function. And so I like using register 18. I use that one a lot. Okay, so register 18. Now this value I put into TCC R1B. TCC R1C, remember, was all 0, so I don't have to load anything to R1. It's already 0. And then this value F4, remember that was part of the output compare register that we needed. That's the high byte, and so we put that into register 18, and then load so we copy or we store this into memory, into this memory location, OCR, output compare register 1A high byte. Then we do the low byte. We load that into register 18. So I just use register 18 all over the place here. And then that way, if I just keep the number of registers, for me, if I just keep the number of registers that I use down to a minimum, then I don't have to worry about keeping track of a whole bunch of different things, and I have more versatility. Okay, so there's the high bytes that I've loaded in and the low byte. Next, I write this value. This is the value I needed to put into the timer interrupt mask register 1. So I load that in. And so remember that one sets up my interrupts to be the output compare interrupt enable for register 1 for timer 1A. So that's what that's setting up there. Okay, and then I take this value, and I want to write that into my data direction register. Okay, and so I load this value into the data direction register. Basically, that sets up pin 6 as an output. So we take this value, we put that into register, the data direction register. So notice, in order to use the out command, I have to offset the data direction register by 20. Okay, so that gives us the I/O address. And it definitely does make a difference. All right, so we need to just keep that in mind. When we use out and in, we have to offset by 20. So we put that value in, and that basically makes our pin 6 an output. I now load this value into port D. So again, here's an out to port D, and I have the offset. So this value basically sets pins 2 through 5 up to set up their pull-up resistors, so that our circuit does not require pull-up resistors. Okay, and I load that into port D. And now I'm going to read from pin D. So notice again I have this offset. I'm going to read from pin D, and I'm going to take that value and I'm going to AND it with these values so that this masks off pins 2 through 5. Okay, and so if you remember, that's what we called X in our theory, and so I'm going to now put that value into the passed value. Okay, and so that allows me to have a passed value for X. So when I actually get the first interrupt, I actually have a value there to work with. All right, so that is the setup routine, and then I enable the interrupts, and then I leave the setup routine. So this is the full content of the setup routine. Okay, then we have our loop function, which again basically does nothing, and now we have our interrupt service routine. So this is actually a fairly simple program. I wish I could show this whole thing on one screen, but I can't. Okay, well, we'll do what we can. Okay, so here is our interrupt service routine vector as our label. And so the first thing I do in this function is I want to save whatever may be used by this function so that I can return it back to the original state when I'm done. So this is very important to do in an interrupt service routine. It's very important to save whatever variables you use. Even though register 18 and 19 can be left messy in a function you can do that. In an interrupt service routine, you don't want to do that, because basically what happened is you could have some function in general that is using all the different registers, and it's in the middle of using a register when an interrupt occurs. So maybe it's in the middle of using register 19, and an interrupt occurs. When it comes back, register 19 is messed up. That messes up the program that was running in. So it's always a good discipline to save any variable that you're going to use so that when you return from the interrupt service routine, the state of the system is exactly as it was when it entered the interrupt service routine, except for whatever changes the interrupt service routine did. Right? So the first thing is I save. I'm going to save here R0 and R18. So I push those. Okay. Now R0 actually I don't plan on using, but I'm going to go ahead and save it anyway. That's just a good practice. Maybe it's superstitious to do that, but anyway. So push R18. I'm going to be using R18, so I'm going to save it by pushing it onto the stack, and then I'm going to load the status register into register 18, and I'm going to push that onto the stack, and then I'm going to push register 19 onto the stack. So these are all the things, definitely registers 18, 19, and the status register I'm going to be using. So I'm going to push them all onto the stack as a temporary storage for them. Okay? And at the end of my routine, I need to pop them back off and put them back in their appropriate places, those values. Okay? So if I go down here at the bottom of my program, you can see I have to pop them off. So remember, 19 was the last one pushed, so that's the first one popped. Then I pop register 18, which I put back into the status register. Then I pop register 18, pop register 0, and return from interrupt. Okay, so those kind of bookend my subroutine. Okay, so All right, so there's my subroutine. So that's the first thing I do. Before I do anything else, that's what I do. Now, the next thing I do is I input into register 18 the value of port D, or pin D. Okay, so remember I have the offset there. That goes into register 18, and then I AND register 18 with the mask that just isolates pins 2 through 5. So that's what this is doing. Okay, so I put that into register 18. Into register 19, I put the past value of this, and that I call port DP. I put that into register 19. So in register 18, I have the most recent value of what's happened here. In register 19, I had the past value. And then I load register 18, which is the present value, into the past. So now I have read the past, and now I have reset the past. So what is present the next time around through what the next time the service routine is called will be the past value. And so I've stored that there in that register, in that memory location that's allocated for that variable. So I now have the present value in register 19, register 18 rather, the past value in register 19. Okay, the past value. Now I'm going to exclusive OR registers 18 and 19. So what does the exclusive OR do? So I have the past value and the present value, and I exclusive OR them. If there are any changes, for any bit that's changed, I'll get a 1. Any bit that's the same, if it's a 1, if both of them are 1s, that's the same, I'll get a 0. If both of them are 0s, I'll get a 0. And so if there's a change, I'll get a 1. So that's how we indicate a change. Now, if both of these are identical, so the bits themselves may be 1s, they may be 0s, but the question is, if they're identical and you exclusive OR them, you will get all 0s. In the event that you get all 0s, then the Z bit will be set and branch if equal. That will, so if they're equal, then when you take the exclusive OR, you'll get 0. That'll set the Z bit. This branch is based on Z, and that will go to this place, clear bit 6. So that will take me over to this place over here. Okay, so remember that's one of the places I want to go, or rather, that's one of the cases where I want to clear the bit. And there are 5 cases: when you have all 0s, or when you have 1 in each of the possible bits. Okay, so the first time I check if they're all 0s, I go to clear bit 6. Now, when I do this exclusive OR in register 19, I now have what I had previously called Y in my theory. Okay, and so now I'm going to compare immediate register 19 with the value 20. Now, when I do that compare, it's going to see if what's in register 19 is basically this number, which corresponds to having bit 5 set, and it does so in a way that does not change register 19. Okay, doesn't change register 19, so it leaves it intact. So if what's in register 19 is equal to 20, then I'm going to go to clear bit 6. Simple. I can now compare register 19 with this value. This is the value of having bit 4 set. And again, it leaves register 19 unchanged. If register 19 is equal to this quantity, I'm going to go to clear bit 6. If, in this case, so I have all of these cases. This is bit 5, this is bit 4, this is bit 3, this is bit 2. And so in each case, if any of these are set, I'm going to jump over to clear bit 6. Okay, so it's actually a fairly simple routine to check if 2 or more are set. And actually we do it by checking if 1 or less is set. And that's what we're actually doing. So it's the inverse. And so if by this point we still have not jump to clear the bit, that means we're going to set the bit. And so here we do set bit immediate. Okay, and so port D, pin 6. Okay, I'm going to set port D, pin 6, and I'm going to jump to done. Okay, so it's actually just going to skip over this, an R jump. So clear bit 6 is instead of setting the bit, I'm going to clear the bit 6. Okay, and then I'm going to continue on, and my done portion then is I'm going to restore all my variables. So I've done what I need to do. I either set the bit or clear the bit, and I've done that now. And so I'm now going to restore the registers and return. And that's it. That's the program. That's all there is to it. I mean, there's a lot going on, but it's all very reasonable. It does exactly what you tell it to do. This is the hardware that I'm using for this project. So for this project, I have my Arduino, and I'm taking pins 2 through 5 of the Arduino, and I am connecting them through wires onto my breadboard. And the breadboard then, on the breadboard, I'm connecting to this dip switch, dual inline pin switch. This particular one that I have has 10 pins associated with it. The important thing is that I can easily switch multiple pins at a time. And so they go through the switch, and then these guys are for ground. Okay, so this is ground. This ground comes from ground on the Arduino. And then pin 6 comes through this long red wire down here to the breadboard, goes through this resistor right here, and goes to one side of my LED. So this is my LED, and then the other side of the LED comes back here to ground. Okay, so whenever that pin 6 is 5 volts, the LED will light up. Okay, so I have successfully downloaded my program onto the Arduino, so it's actually currently running right now. It's not obvious, but remember I mentioned that the state that you're most likely to be in is the state when you're all zeros. That is, there's no change. So as long as you've been watching, there's been no change, and so the light has been dark. So now I'm going to flip a couple of these switches. The light goes on for 1 second. The next second, when it checks, there has been no change, and so it goes off again. Okay, so basically what happens is every time I throw a couple of these switches, it goes on for a second and then off. Okay, and I can throw them in different combinations. Okay, so that time I threw 3. So notice I threw 1, didn't do anything. I can do any one, and it doesn't do anything. But if I do multiple, then it goes on, and it goes on for 1 second. So we have successfully made this project work from start to finish. Thanks for watching.